Hey everybody, and welcome to this video on solving two-step equations. So, let's get the show on the road. Alright, so we've already solved all sorts of equations. Some required one step of just adding or subtracting a number to isolate a variable, and some involved just one step of multiplying or dividing in order to solve a variable. And just for a quick review, why don't you pause the video and please solve these four equations right now. Alright, not so bad. And what we're going to explore right now are equations that are going to require both addition and subtraction and multiplication and division. In fact, they're going to involve first adding or subtracting a number just so we can get an equation similar to these two right here that will then require multiplication or division to finish. So consider the equation 3b plus 5 equals 17. Now, we haven't seen an equation like this before. But we have seen equations like 3b equals some number. So if we could somehow take this original equation and make it look like that, we'd be home free. We know exactly what to do. Well, I absolutely think we can get there, no problem at all. If we subtract 5 from both the left-hand side of the equation and the right-hand side of the equation, we end up with the new equation 3b equals 12. And we absolutely know how to take care of that. Either divide both sides by 3 or multiply both sides by 1/3. And so we found our solution to be 4. One note, whenever you're going to do any step to an equation, please write every single step out vertically. And please write each line below the previous line. Let's check our answer quickly. Awesome, our solution checks out and we determine that b must equal 4. Let's try another. How about 5 equals 4m minus 3? Again, this is unlike any of the equations that we've discussed so far. But if we had an equation that looked like some number equals 4m, well, we know exactly what to do. We'd have no problem with that. Well, my claim is we could easily get from here to here by simply adding 3 to both sides of the original equation. And now we're left with a much simpler equation. 4m equals 8, and we absolutely know how to take care of this. Either divide both sides by 4 or multiply both sides by 1/4. And we find our solution to be m equals 2. Again, we're writing out every single step in our equation solving process as a new line. And we're writing each line below the line before it. Again, let's quickly check our answer just to make sure we didn't make any mistakes. Awesome. And we determine our solution is 2. Alright, here's an example that highlights a potential pitfall when solving these two-step equations. So 2w plus 6 equals 12. At this point, perhaps we know how to take care of this the right way. We haven't seen this type of an equation before, but we have seen equations like 2w equals some number. So how do we get this first equation to look like this? No problem. Let's subtract 6 from both sides of the original equation. And now we've got the much simpler equation, 2w equals 6. We can divide both sides by 2 to isolate w. And we find the solution to our original equation to be 3. And with a quick mental check, if we substitute 3 in for w, that equation will be made true, so 3 is indeed our solution. Now, when you look at the original equation, and you see a 2w, and you know that eventually you want to have a 1w at the end, it may be very tempting to first divide by 2, so that instead of 2w, you've got 1w. Now, I wouldn't suggest it, but if you do, you have to be very careful. You have to divide the entire left side of the equation by 2 and the entire right side of the equation by 2. And this is what that would look like. We end up with the new equation w plus 3 equals 6. We divided both the 2w by 2 and got 1w, And we also divided the 6 by 2 and got 3. It's kind of like saying, if I have 2 apples and 6 oranges, and I only want half of that, that's going to be 1 apple and 3 oranges. You take half of the apples and half of the oranges. And from here, obviously, we're going to subtract 3 from both sides and we'll get the same solution, w equals 3. Now I'm going to show you a pitfall that I've seen some people make before. They see this 2w in the original equation, they know they want to have a 1w, and what they do, they simply divide the 2w by 2 and the 12 by 2, and they disregard that 6 altogether. And this is what that looks like. So note, that was an illegal maneuver because they didn't divide the left side of the equation by 2. They only divided part of the left side of the equation by 2. It's like saying, what's half of 2 apples and 6 oranges? 1 apple and 6 oranges. No. And look what happens when we finish solving this equation. We get the solution w equals 0. If we substitute 0 in for w in our original equation, it absolutely will not make it true. So you know there's been an error. So I really wanted to put that on your radar to say, if you want to divide first, you got to be really, really careful. What I would suggest is first, add or subtract numbers so that you get one of these one-step multiplicative equations, which we absolutely know how to solve. And so, my suggestion as a general strategy when solving an equation that's going to involve both addition and subtraction and multiplication or division, first, add or subtract a number from both sides of the equation so that you have a one-step multiplicative equation left. You got some number of variables on one side and just a number on the other. Second, divide or multiply both sides of the equation in order to actually isolate that single variable and solve the equation. Third, check your solution. All right, time for some practice. Why don't you pause the video and solve this equation, and when you're done, play the video and I'll walk you through it. All right, so per usual, the first thing we want to do is isolate this -5/7 k and have just a number on the other side of the equation, because once we're there, we'll absolutely be able to solve it, no problem. So to do that, let's add 3 to both sides of the equation first. Now all we need to do is multiply both sides of the equation by the multiplicative inverse of -5/7, namely -7/5. All right, not so bad. We found our solution, k equals -21. Now, there is another way we could have handled this equation. And if you really don't like working with fractions, that's okay. Sometimes we have to work with fractions. But there's a way to do this equation without necessarily using so many fractions. And it's using a strategy called clearing fractions. So, to clear the fractions from an equation, with only one fraction in it, in this one, -5/7, if you multiply both sides of the equation by that denominator, then we'll be left with only integers. So check it out. If we multiply both sides of the equation by 7, now we're left with an equation involving only nice integers. It's still a two-step equation, but no problem. First things first, let's add 21 to both sides to isolate this -5k. Then, let's divide by -5 on both sides to isolate that k and solve the equation. Boom, we got the exact same solution. Now, this equation wasn't too tough. I mean, it had a fraction in it, but it wasn't so bad. But if we have an equation with a whole lot of fractions in it, like these two, I don't really want to work with all these fractions. I mean, we'll probably be able to do it anyway, but it could be really confusing. So why don't we try to clear them? And to clear the fractions from an equation with multiple fractions in it, just multiply both sides of the equation by the least common multiple of all the denominators in the equation. So for this first equation, I see a denominator of 4, 2, and 3. Their least common multiple is 12. Let's multiply both sides of this equation by 12. And now we're left with a much more user-friendly equation, and I bet you could solve this all for yourself. Why don't you pause the video and finish solving this equation on your own, then play the video, and we'll check your work. All right, Not so bad. For this next equation, the least common multiple of these three denominators is 15. So if we multiply both sides of the equation by 15, hopefully we'll get a new equation that'll be a lot simpler and won't involve fractions at all. Alright, life is groovy. We got a nice equation with no fractions at all. Why don't you pause the video and finish solving it? Alright, here are some more examples that are going to highlight another time-saving strategy. So the first thing I notice is that we've got 3 times the quantity of w minus 9. And our first impulse is probably just to use the distributive property and multiply that 3 by both the w and the negative 9. And no problem with that. And that leaves us with the equation 5 plus 3w minus 27 equals 47. Before we do anything, let's combine that 5 and the negative 27. 5 minus 27 is negative 22. So we've got 3w minus 22 equals 47. And from here, I hope you know how to solve this equation. Alright, life is groovy. We found our solution, 23. But there is another way to solve this. Now, of course, we're ultimately trying to isolate w. So we get w equals a number and we solve the equation. But what we're going to do in this second example is we're actually first going to start by trying to isolate w minus 9, as though it were its own variable itself. So to do that, what we're first going to do is subtract 5 from each side of the equation. Remember, we're still trying to isolate w minus 9, so what we'll do now is divide by 3. And I'm sure you know what to do from here, and we end up with the same solution of 23. Alright, now, those weren't so bad. But imagine that this 3 in both cases were something like a nasty fraction. I don't know, maybe 5/7 or something like that. Now, we may have the impulse to go ahead and actually distribute this 5/7 to both the k and the negative 2012, but that's going to leave us with the equation 23 equals 8 plus 5/7 k minus 10,060 over 7? Oh gosh, I mean, I don't know, man. That just doesn't look very good to me. I don't want to deal with that. But if instead we decide to isolate what's in the parentheses, the k minus 2012, life might be a little bit easier. Let's see. First, let's subtract 8 from both sides of the equation. And now, let's multiply both sides of the equation by the multiplicative inverse of 5/7, namely 7/5. And whoa, check it out. We got this very nice equation. 21 equals k minus 2012. I bet you know what to do from here. And we find our solution to be 2033. Now note, that would have been the solution if we had done it this other way as well, but that just looks like it would have been a lot tougher, and this way wasn't so bad at all. Alright, that's it. Time for some practice. We got 4 equations in front of you. Why don't you pause the video, please solve all 4 of them, and play the video and see how you did. Alright guys, that's it for this video. I hope you found it helpful, and I hope you enjoyed.